Good afternoon. I'm Alastair Hales from the Electrochemical Science and Engineering Group at Imperial College London. I'm going to talk today about the cell cooling coefficient, its requirement in the battery industry, how we may use it in application, and how the cell cooling coefficient can be used to improve cell design in the future. I will begin with some background before moving to the concept of the cell cooling coefficient. I will then present our most recent work about how we can use the cell cooling coefficient to impact cell design. Heat generation occurs in any lithium-ion cell. It is dependent on many operational characteristics and is highly nonlinear. As a result, temperature rise is always an issue, and thermal management is an absolute necessity. In lithium-ion cells with poor heat rejection pathways, the ones that cannot be effectively thermally managed, we see high temperatures and high temperature gradients. These lead to accelerated degradation and can become a safety risk. Despite these facts, thermal performance of a lithium-ion cell is often overlooked when battery pack designers choose the cells for their pack because there is no metric which defines thermal performance on a cell datasheet. They typically select cells based on the performance metrics available to them and so end up choosing the ones with the highest energy density. As a result, cell manufacturers must prioritize energy density to remain competitive in the market. This is a problem for thermal performance because active material is thermally insulating. Temperature gradients and therefore degradation will be greater in an energy-dense cell. Battery pack designers attempt to combat the problem with over-engineered thermal management solutions. They are heavy and demand lots of power. Only 64% of the Tesla Model 3 battery pack is lithium-ion cells. Thermal management system makes up most of the remaining mass. At cell level, energy density may be optimized, but at pack level, it certainly is not. We want to provide the tools to help industry move away from suboptimal thermal management, and we want to do this with more information on the cell datasheet. Today, you will find energy density and most probably power capability, but you won't find any information on thermal performance, and this presents a real problem for the engineer attempting to design the thermal management system. We propose the inclusion of a thermal performance metric on cell datasheets in the future. A universal measure of a cell's capability to reject heat will better arm the battery pack designer with information to optimize the design of a thermal management solution. In time, the cell cooling coefficient can become a metric for cell designers to enhance and a standard against which all cells can be compared. For the purposes of this presentation, we are going to focus on pouch cells. They are made up of layers of electrode stack in a sandwich-like format with tabs that are connected to each layer. Pouch cells can be cooled through their tabs, but surface cooling dominates in the battery industry today. Surface cooling is highly effective for bulk heat removal from the cell. The problem is the direction of heat transfer in the cell leads to temperature gradients between each layer. These cause non-uniform current flow and accelerated degradation rates. Tab cooling can solve these problems because heat is instead transferred along the layers of the cell towards the tabs. The problem is the amount of heat that can be removed through the tabs. They are a significant thermal bottleneck in many cell designs that exist today. The benefits of tab cooling can be considerable. Our group has published data presented in this graph. It shows that the lifetime of the cell can be tripled by tab cooling. I'm going to introduce two example cells. Cell A has large tabs located at opposing ends of the cell. The tabs are quite big compared to the size of the cell, and it appears to be suitable for tab cooling. Cell B, meanwhile, has small tabs located right next to one another. It appears to be entirely unsuitable for tab cooling. The problem is we cannot say any more than this. We have no way to actually quantify either cell's capability to be either surface cooled or tab cooled. Every one of the parameters shown in these two tables would have a part to play. Often, cell disassembly and many characterization experiments would be required to populate such tables. The cell cooling coefficient is designed to try and solve this limitation. What we really need to know is what temperature gradient would be required across our cells to remove a certain amount of heat. And so the cell cooling coefficient is designed to provide exactly this information. We divide the rate of heat rejection from the cell by the temperature gradient incurred across it. We believe the cell cooling coefficient can become a tool to estimate the rate of heat rejection for a given thermal gradient, a constant for a particular cell and surface to be managed, a metric against which any two cells may be compared, and a standard for competition and improvement. The cell cooling coefficient is empirically derived and requires no prior knowledge of the cell composition. Other thermal performance metrics have been borrowed from other areas of engineering. Both the Biot number and thermal conductance actually define a body's capability to transfer heat from one point to another. This isn't all that relevant for a device that is generating heat from throughout its volume. We did need to know all this information before we could try to quantify operational thermal performance. With the cell cooling coefficient, we can reduce this right down and quantify thermal performance with two values for each cell. In a recent study, we looked at the tab cell cooling coefficient for a number of different cell models. Each cell model was similar, except for the number of layers in the electrode stack, represented on the x-axis of this graph. Variation on the number of layers isn't what I'm going to focus on here. Actually, we found that from these 5 cell models, 2 of them, the 3.2 ampere cell and the 4 ampere cell, had thinner tabs. The differences are shown in the left-hand table below. And the effect on energy density is shown in the right-hand table. By increasing the thickness of tabs, we reduce the energy density by less than 1% at the cell level. The benefit in terms of thermal performance is substantial. We calculate that the tab cell cooling coefficient can be increased by 20% if the thicker tabs are selected for the 3.2 ampere cell. That's not a bad payoff, and it comes back to optimization of pack level energy density, not cell level energy density. With such an increase in thermal performance at a cell level, we'd anticipate a simplification in the thermal management system and an increase in pack energy density. Tab cooling can be enhanced by thickening the tabs of any cell. And a thicker electrode stack benefits tab cooling because it increases the cross-sectional area through which heat is removed. Therefore, tab cooling is theoretically unlimited by cell thickness. This is great for the modular prismatic cell designs that are beginning to dominate R&D presentations at conferences in 2020. Surface cooling, meanwhile, is limited by cell thickness. Temperature gradients are inevitable. Surface cooling is fundamentally flawed. There is no escape from the problem whilst it remains the dominant thermal management technology. We will continue to see very large and thin pouch cells cooled through a single surface. Every cell will have a ceiling on its lifetime, which will not be breached until the inherent temperature gradients are somehow reduced or eliminated. We strongly believe that tab cooling is the answer. Yes, it throws up complications with actually implementing the thermal management onto the cell because the tabs are also required for the cell's electrical connections. However, the industry is expected to triple this decade and grow 10,000% in the coming 30 years. It's worth getting this right now. There's no downside. The incremental advances in cell chemistry continue to trickle down to the end user, regardless of how the thermal management strategy is implemented onto the cell. Thank you very much for taking your time to listen today. A big thank you to all my colleagues in the ESC group at Imperial College London.